Hi, everybody. Welcome back to Dave's Math channel. This is my continuing feature on the Math Lovers book, my 3-volume series I wrote from 2019 to 2022, in case you guys are interested. Each of these volumes is available on Amazon.com and be both paperback or Kindle. You can search for my name, David Tier, or the Math Lovers book, in case you're interested in buying any of these volumes or the whole set. Anyway, that's just my pitch for my series. But today I'm up to section 4.3 of volume 1. This is my third video on this section, which is on complex arithmetic. And today I'm going to talk about complex conjugate, complex norm, and complex absolute value. So anyway, let's begin. All right, so these are things that are unique to complex numbers, pretty much. And they turn out to be very useful concepts, all of these. And they all have kind of simple geometric interpretations, which I'll get to at the end. So the complex conjugate of a number, if you have a complex number z, which you can always write as x plus iy, where x is the real component and y is the imaginary component, then its complex conjugate, which we denote as z bar, we put a bar over the z. There's actually two conventions. Sometimes people use a star, an asterisk. I prefer the bar. It's kind of funny. I think people in physics use the asterisk for some reason, but mathematicians prefer the bar. I prefer the bar. guess I consider myself more of a mathematician than a physicist, even though I did study a lot of physics. But anyway, z bar is defined to be x minus iy. So it's really just the same complex conjugate number, except the imaginary components reflected about the x-axis. And I may as well just skip to the picture here. Here's a picture. So yeah, they say a picture's worth 1,000 words. So you can think of z equals x plus iy. You remember I told you a couple lessons ago, you can think of this as a vector. If you think of a complex number as a vector in the xy plane, which again represented as an arrow, then its complex conjugate is just the vector that's reflected about the x-axis from the vector you started with. Z bar equals x minus iy. That's the geometric interpretation of the complex conjugate. And I guess I might as well explain a little bit more on this picture. There's actually two different ways you can represent complex numbers, and they're both shown here. There's the rectangular representation, or Cartesian, if you like. Z equals x plus iy. You can think of x and y as the rectangular, the coordinates. So, you have this little dash figure as a rectangle. And you can always represent a vector that way as the vertex of a rectangle with one of the vertices at the origin. But the other way you can represent a complex number is you can represent it in what's called a polar form, which turns out to be r e to the I phi. Here they're using phi. Usually people use theta. I don't think there's a standard convention for the angle, but it's just r. A simple way to think of it is r times cosine phi plus I sine phi. There's a very famous identity called Euler's formula, or Euler's equation, that says e to the I phi is equal to cosine phi plus I sine phi. I'll get to that in a few lectures. But anyway, so we can write it in terms of r and phi. That's the polar representation. And if we do it that way, then we can represent the complex conjugate is the vector, if you like, or the complex number with the same value of r. R is what's called the absolute value. It's a distance, and you can think of absolute value. This is, I think, a more useful way to think of absolute value. Maybe when you were learning absolute value in high school, you probably just learned it for real numbers. In that case, it's just the value of the real number regardless of the sign, and you might have wondered, why are we learning this? Well, I think a better way to think about absolute value is a distance from the origin. And this notion of absolute value can be generalized to complex numbers. That's why it's useful. Think of r as the distance, or the length. If you think of this complex number as a vector, then its length, or its norm, as it's usually called in terms of vectors, is r. It's just the length of the complex number, and it's the that's what's called the absolute value. And there's formulas for it, and I think I wrote them down here. The maybe I should just back up a bit. There's another thing called the norm of a complex number, which is almost the same thing. The norm is actually just the square of the absolute value. It's r squared. And that turns out to be x squared plus y squared. That's really just a consequence of the Pythagorean theorem. I mean, if you look at this diagram here, you can see that the x component of r of z equals x plus iy is x, and the y component is y, so we have a right triangle here with legs of length x and y, and we know that the hypotenuse has length r, therefore r squared equals x squared plus y squared. Well, since r squared is x squared plus y squared, if you want to get r, which is the absolute value, just take the square root. So the absolute value of a complex number given in rectangular coordinates x plus iy is equal to the square root of x squared plus y squared. And that's a very useful quantity. And you can verify, it's very easy to verify that this reduces to the familiar absolute value when the number is real. Because if the number you're starting with is real, then y is 0, and then you just get the square root of x squared. Well, the square root of x squared is also the absolute value of x. I mean, if x was negative, it would be the negative of x, but if x was positive, it would just be x itself, positive or 0. So that it does reduce to the familiar absolute value in the case in which your number is real, but in the case in which the number is imaginary, it's the length of the vector that it corresponds to. So that's complex conjugate, norm, and absolute value, which are very useful quantities to work with when working with complex numbers. And we'll see how they are useful. In particular, I haven't talked about how to divide complex numbers yet, but it turns out that the complex conjugate, these concepts will come in handy when we're coming up with a formula for dividing two complex numbers. We'll use the complex conjugate as well as the complex norm or the complex absolute value, if you like. So anyway, that's complex conjugate, norm, and absolute value. Thank you for watching. Long live math, and I'll see you guys next time. Bye.